Good day, everyone. My name is Wilczek, and I'm an audio developer at Loudly, and also I'm the founder of an educational company, Wolfsound. And today I would like to talk to you about the combination of differential equations and neural networks for virtual analog modeling. So I'm very thankful for the previous presentation because it already sets the stage. And this work is an extension of my master's thesis, which I've done at the University of Erlangen-Nuremberg under Professor Emanuël Habets. And the bulk of this work was done at the Alto Acoustics Lab with Alec, Wright, and Vesa, Välimäki. The audio examples, a lot of them can be found at dwolfsound.com/publication/DAFx20in22. The problem that we're trying to solve, as was already said, is we try to model analog audio effects in software, and this is termed virtual analog. And in the recent years, we've seen a successful application of deep learning to this field. So where in the general deep learning field, we had this long short-term memory architecture. We also seen that in virtual analog modeling. The same goes for a residual network, which was used to model the residual of the state space, and this model was termed state trajectory network. And then in the deep learning world, it was found out recently that actually a residual network is a particular case of a much broader category of neural network architectures that also involve differential equations. And the study of this was termed ODE-net or node, and exactly this work attempts to adapt this concept to virtual analog modeling. So to kind of show how this method fits in, let's maybe revise this successful state trajectory network model. There we have, at each iteration of the model, we have the current input, so the input sample to the model, and then we have the previous state vector, which describes the state of our system at a particular time point, and we feed it into a neural network, which produces a residual of the state space, which is then scaled by a factor that depends on the sampling rate, and it's added to the previous state vector to produce the current state vector. And this current state vector is then retained for the next iteration. Well, if someone is well-versed in ordinary differential equations, this looks very much like the forward Euler scheme of solving numerically differential equations. Well, here we have the previous input and the previous state vector, which is fed into a derivative function, and then the whole processing is kind of similar. So if these two are so related, maybe instead of using the derivative function, maybe we could replace it by a neural network, and during processing, this network would also learn the derivative function of our system. But now when we see this, like, why should we just narrow down to just the forward Euler? Maybe we can replace it with any numerical solver and achieve even more generality. So exactly this was the idea behind this work, to adapt this concept to virtual analog modeling and compare it to other models, taking a number of different criteria into consideration. So let's take a look. How does a numerical solver typically work? It always wants a vector of time points for which we want to estimate the output of our system. It needs some initial state, this vector y0, and then it normally receives a derivative function which depends on time, which makes it implicitly dependent on the input signal, and it also depends on the state. So in our case, we replace this function f, the derivative function, with a neural network. And to make it memoryless, we decided to use a multi-layer perceptron. And for the initial value, we decided to supply the ground truth, actually, at training time, which is called teacher forcing in the deep learning literature. But then at test time, we cannot use ground truth, so we used an all-zero vector. And then to access the input signal at every possible point in time, we use linear interpolation. So that's how our architecture actually works. And let's consider it for just a single example from the data set. So the example consists of a series of input samples and the target sequence of the output state vectors corresponding to these input samples. And one of the entries of the state vector is our audio output that we can actually listen to. So before each example, we set the initial value, and then we invoke our machinery. And this machinery sets the excitation data to the derivative network, because it then needs to use this information during processing. And then we invoke our solver loop. And this solver works iteratively. And in each loop, it can invoke our neural network. And it can do so for actually any point in time with any given state vector. So we cannot predict it in advance to keep this generality of the numerical solver. Then the derivative network obtains the value of the input signal at this desired time point, and then returns the estimate of the derivative. And the solver, at the end, produces exactly this series of estimates of the state vectors. So to actually see whether it actually works, we wanted to try a very simple model, and I'm happy that it was already shown on the slides today. This model has just one state. It is y1, and this is our audio output. And what's nice about it is that it has a known closed-form derivative function that we can compare against. Our dataset consisted of 8 minutes of guitar and bass recordings, synthesized with the SPICE software at 44.1 kilohertz sampling rate. And for the training, we used the error-to-signal ratio on pre-emphasized signals, plus a DC loss term, because we want to suppress the DC component in the audio output. And here are the architectures that we compared. So we took the successful LSTM-based approach with 8 memory cells, then also the state trajectory network with 3 layers, and also ODE-net, so our approach with 2 layers and the forward Euler scheme, and also with the implicit Adams scheme. And then for the comparison at test time, we use a different metric to ensure that we don't just learn the loss function. So we use the signal-to-distortion ratio. And here you can see our results. So what this basically says that actually we can use this model for visual analog modeling. We can also observe that actually when we increase the sampling rate significantly, with respect to the training sampling rate, we can actually obtain a lower error, and we can outperform some architectures that cannot be adapted to different sampling rate processing. And then we also shown that we can actually achieve comparable performance to the baseline, but actually this ODE-net here uses fewer parameters, which is always desired to have small networks. And then you can also see that we obtained aliasing for this 22 kilohertz sampling rate, which is kind of what could be predicted because we trained the model at a higher sampling rate. So let's listen to a few audio examples. Here's the input to our model. So here's the desired output. And here is the output of the LSTM at 44.1. And the ODE-net 9 with the forward Euler scheme. To gain some more insight into the model, we decided to visualize the learned derivative. So on the right-hand side, you can see the closed-form solution. And on the left-hand side, you can see the derivative function that our neural network learned. And as you can see, it's much smoother, probably thanks to the fact that the dataset was already band-limited. But thanks to this smoothing, we don't run into the problem of the stiffness of the differential equation. So then we decided to try this model with a more advanced one, surprise, surprise, so the second-order diode clipper, which has an additional state, Y2, the additional capacitor. And then we used, for the training loss, just the error-to-signal ratio, and compared the similar architectures, but this time they needed to be larger. And the third one, this ODEnet20, had specifically 2 times fewer parameters than all the other networks. And we use also 3 different numerical solvers, so the forward Euler, the trapezoidal rule, and the explicit Runge-Kutta of order 4. And we use also the SDR to compare these models. So let's take a look at the results. So as we can see, our model performed worse, but not much worse, we could say. What's interesting here is that actually, when we have the same derivative network, neural network architecture, but we increase the level of complexity of the solver, we can actually obtain better results. So we can have this trade-off here. And then also, we learned that a smaller neural network, the one that has 2 times fewer parameters, ODEnet20 RK4, can outperform a larger network with a simpler numerical scheme. So let's listen to examples. Here's the input signal. Here's the desired output. And here is the LSTM at 44.1. And here's the ODEnet30 RK4 at 44.1. We also visualize the derivative. And what's nice about this visualization, you can see that actually the neural network learned a little bit of this asymmetrical behavior of the second-order diode clipper. And also, it shows that it's not so easy to derive this derivative actually analytically. So that could be a potential benefit of using a neural network for this. What are the shortcomings of this approach is that we failed actually to teach this architecture a phasor. Then it also needs severe regularization not to plateau and diverge during learning. And we also seen that it's susceptible to numerical issues, so you need to rescale the learned differential equation. And finally, we haven't provided any actual real-time implementation, so this could be a field for future work. To conclude, we actually shown that a neural network can learn the ODE, which governs an analog audio effect. And then that this neural network actually doesn't need oversampling during numerical solutions, which is an advantage over closed-form solutions. Then we also shown that if we increase the sampling rate, our model is still valid. What's not always the case for neural network-based models, but it can actually increase its accuracy, so after the training. And then we also shown that we can provide results that are comparable to established successful architectures, but we can do so using fewer parameters. And then also we've seen in the visualizations that the learned derivative is actually physically interpretable, but we did not need to derive it analytically, what also can give us some more insight into the circuit. And finally, that the derivative that we learned can be used with any numerical solver, and in this way, we can trade off accuracy for performance and also the neural network size for the solver complexity. So this gives us more flexibility. And if you want to listen to more audio examples, then you can go to the specified website. And at this point, I would also like to thank the organizers of DAFx and Audio Labs for actually enabling me to be here in person. So thanks for your attention and invite your questions.
While we take questions, could the next speaker come up to get fit for their microphone? Yeah, in the middle there. Could you pass this back, please?
Hello, thank you for your talk. I was wondering if you have, for some circuits, you can't reduce to an ODE. You have algebraic constraints. Have you thought about how would you include such constraints in your method?
Sorry, I cannot hear very.
How would you
good.
include algebraic constraints for circuits that cannot be reduced to simple ODE?
So the question is, how would I include algebraic constraints to this model?
Yes.
Well, the underlying idea is then with this approach, we don't need to deal as much with algebra. But I'm not sure if I get your question right, because you then assume that we learn this all the necessary relations from data.
Yes, but for some circuits which has dissipative components and algebraic laws like diodes or vacuum tubes, etc., depending on the topology of the circuits, you cannot reduce your equation to an ODE. It's an algebraic differential equation. So in this case, how would you?
Okay, so then I would think about like. First of all, deciding like what's the content of our state vector, so what we actually look at the states, and then I would focus on providing actually state-rich data so that we cover actually the whole space of the possible values of these states. So that's how I would approach this. And this, of course, has some drawback because you need to then like know the circuit and actually measure this data and decide like what's important, what's not, and what's not. But then I guess you have a chance to skip this. But other way of including algebraic constraints actually don't come to my mind because I've not run into this problem, I guess.
Okay.
Thanks a lot.
Yeah. So my question would be about data. So you said you took 8 minutes of training data. So it was just one specific domain, so electric guitars or guitars, right?
As guitar and bass.
Guitar and bass, yeah. I just wanted to know how you can make sure that this generalizes over every input, let's say, that it behaves like the real thing.
So actually this was based on previous work that was done by Alec. So actually in that work, they took like a long data set and then they observed the validation error, right? How the validation error decreases with the increasing size of the data set. And they, like for their model, they discovered it's actually 2 minutes sufficed to achieve like the non-decreasing validation loss. So the same assumption was used here, and it's also how it was used in the previous work.
Yes, thank you for the presentation. I have a related question and a following one. My question was, I did not get exactly what are the training data. If the target signal that you use in a supervised way is in fact provided by the numerical solver, the basic numerical solver. And the second question is that how do you check that what is learned is in fact the derivative function and not the results in a perceptual way? I don't know if you get my question, but you...
So the first question, as I understand, like you ask, like where do we provide the target data, or?
It's exactly what are the data you use for training? What is the target data and the input audio?
So what we do, we have this 8 minutes of guitar and bass. This gets synthesized with the SPICE software, and then we split it into the test time, 20%, and the training set, 80%, which then again gets split into the training set and the validation set. And then for the training, we split this training data set into sequences which are half second each. And these are still just input and output signals. And then we arrange these short segments into mini batches, and then we proceed with the mini batches, and at each 2048 samples, we do a gradient step. And before the next step, we provide the actual value of the circuit at this point as the initial state, and then we let our network and solver combination to predict the next 2,000 samples.
Okay, but then my question was a little bit simpler. So then you give a pair of signal, the original signal, and the result of your circuit, right?
Just the first sample. Just the first sample.
You don't give the full sequence of...
Just the first sample of the output and the whole input sequence. So like, because we need, obviously, the input signal, and we give the one sample of the output as the initial state. But this is just at training time, because at test time, we have a long sequence, and then we can initialize it with 0, and then just provide the input signal to produce the output signal. Okay.
Okay, we're at time, so let's have one more round of applause for Jan.
Thanks a lot.